Hi, and welcome to this video where we continue our study of ways of representing text as input to machine learning models. In particular, in this video, we're going to look at the CBOW, or the continuous bag of words representation, which I guess is one of the most advanced representations that we're going to see. So again, just to remind ourselves what we've been looking at in the last couple of videos, we've been looking at machine learning tasks on text, for instance, creating a spam filter where the input is a text document on email, like the one I have here. And so we saw, for instance, the bag of words representation of such a text, where one interpretation is that every word in the English dictionary corresponds to a standard unit vector, having a single one in some entry corresponding to that word and zero everywhere else. And then one could represent a document by just summing up the vectors that make up each of the words or the terms in the document. Right. The issue with this representation, as we also tried to discuss a little bit in the previous video with the co-occurrence matrix, is that somehow this representation ignores similarity between words. And at least it would be sensible if the representation, the vector representation of a document, was similar to the representation of another document if we replaced all the words by synonyms to obtain this other document D, right? This is one of the things that we motivated co-occurrence matrices by. Now, of course, right, the question is, how do we define these word vectors, embeddings of words that preserve similarities between the words? And that's the question that we looked at also in the previous video. Right, so somehow we have these words and we would like to do, we have a large collection of text, and we would like to use some kind of unsupervised learning approach to find embeddings or representations of these words that learn the similarities in some sense, right? So here we just have text, right? There's no labels telling us that some words are similar to others. We just have a lot of training text available. And we'd like to somehow learn that these words here are more similar than these words down here corresponding, for instance, to tech companies, right? So, okay, and then we saw the co-occurrence matrix. So I'm just going a little fast since we already saw this in the last couple of videos. But the co-occurrence matrix was the one we saw in the last video, where we have these training documents, and then for every pair of words, we count how many times these two words occur together inside a small window. So these were the so-called co-occurrences. So we count this in the matrix. Then basically we saw the naive representation was then to represent the word, we'll take the corresponding row, and that would be the vector representation. But if we wanted a slightly shorter representation, then we would somehow do an eigendecomposition of this matrix, somehow zero out the small eigenvalues and replace it by a D by K matrix, corresponding somehow to the K largest eigenvalues in absolute value, right? So all of this was in the previous video, but this gives a way of constructing a D by K matrix where every row would then be the embedding of a word. Okay. Right, so this was the co-occurrence matrix. Now, one issue with this representation that we also discussed a little bit is that this is going to be a giant matrix, at least if you have lots of words, right? It has it's basically quadratic in the size of the dictionary, right? So it can be a really large matrix, and it can be slow to compute eigendecompositions in such huge matrices. And also, it also uses a lot of memory just to compute it, right? So there's some drawbacks here. But another issue that we did not discuss in the previous video, but this is also important, is that here we're really handcrafting these features by human experts, right? We just humans have sat down and said that, well, it's probably a good idea to count co-occurrences, right? And just use these counts basically as the representations, right? But if there's one thing that we've learned in this course in general, right, is that often machine learning algorithms are actually better than human experts if they're given enough training data. And this is the, I guess, motivation or approach we're going to try to take here in this continuous bag of words representation, right? So basically we're going to use learning to find good embeddings of words. We're not just going to count or come up with some way of defining features that we as humans have defined. Good. So CBOW, or continuous bag of words, is a way of basically turning this task of learning word embeddings into a supervised learning problem. So similar to the co-occurrence matrix, we're going to have context windows. And context windows are again specified by a width around a word. And we could, for instance, have a context window of width 2 around the word who in this email sentence from an email that I received. So, for instance, here's the word who in the middle, and the context windows are then the two words preceding it and the two words following it. Okay. Now, the learning task that we will be defining in this continuous bag of words idea or approach is that we would like to somehow train a machine learning model, it's a supervised learning model that can predict the middle word there from the context. So predict it from partner, abroad, can, and accommodate. So basically here, the input to, say, a learning algorithm would be, or a hypothesis that we've trained would be the words partner, abroad, can, and accommodate. And then the goal is to predict the label who, like exactly like in the supervised learning setup, right? We'll try to basically have some features, basically here 4 words, and then the label is another word, and we have to learn this word that's the one that's in the middle of this sentence. Okay. So the question is, again, this input here is a sequence of 4 words. So we somehow need to, at least if we want to use the machine learning models we've seen so far, we have to represent them somehow, right? They have to be somehow encoded as feature vectors. And so there seems to be like a bootstrapping issue, right? So we're trying to learn a representation of all the words, but to do so, we need a representation of all the words. So there's some bootstrapping here, but we'll deal with it in a kind of naive, simple way. So the way we're going to represent the input here to this learning problem is just the naive one-hot encoding of basically the one that we use in bag of words. So that means that every single word in the dictionary is just represented by its own standard unit vector, just as a single one in some coordinate and zeros everywhere else. So this could look like this. For instance, the word for there's a coordinate designated to the word for, everything else is zeros. The word can, maybe this is the coordinate for can, this is the coordinate for who, and so forth, right? So which means if I have this whole sentence, right, each of the words, there's the 4 vectors up here are the, I guess, the feature vectors that are kind of the vectors that describe the 4 words that come into the learning task, the partner, abroad, can, and accommodate. Who, I guess, is the label that we want to predict, which is also just a long vector with a single one in it. That's the vector, that's the label we want to predict. Okay. So how do we then generate training data for this machine learning task that we're trying to define? We're trying to define the supervised learning task. So basically, what we're going to do first is we're just going to, construct a dictionary that contains all the words that occur in the training data. So this is just another way of saying, if you don't want to just use the whole English dictionary and have a feature for each and every word, every one of the words, you just scan through all your data and count or figure out what are the words that occur. Give them a unique number each, like 0, 1, 2, 3. Every time you see a new word, you give it the next available number. Right. And now you go over the documents again, and you look at every word in the document. All right. So now you're going to generate a training example where you have this word, and then you have the context around it. And so you let the context be the input features and the word be the target label. And the way you're going to do it is we're just going to one-hot encode all of it as indices into the dictionary, right? So we just counted, basically just gave every word a number from 0 to the number of distinct words that occur. And we're just going to one-hot encode every one of the words in the context window and one-hot encode the target label. So for instance, if this is text here appears in one of the training documents, we reach the word who, then we have this, basically we want to have this feature vector here, a partner, abroad, can, and accommodate, and who is the label. And we also have maybe abroad who accommodate 200 million and can. So we just we scan through all the words that have a context window around them. And we generate all these examples, right? So this comes from all our training data. Maybe we have another training data set where there's somewhere in the middle, this taste of pears is delicious. So pears becomes the label, and this other taste of is and delicious become the features. So now what we're going to do in this continuous bag of words is that we will have a shallow neural network. Okay, so we're going to have a network where on the left, we're going to feed in the context window. So these are the features that are supposed to be used to predict the label being who in this example. Okay, so we have this comes in on the left, and we're just going to one-hot encode all of them. So basically here, right, each and every one of these groups here has one neuron for every word in the dictionary that we collected. And so we're just going to one-hot encode the representation of these 4 words, just going to be a one-hot encoding of partner, one-hot encoding of abroad, can, and accommodate, and we're going to feed it into these neurons in the input layer here. Okay. And we're not going to use any bias in this network. So it's a very simple neural net, no bias vectors. And in the middle here, we're just going to use identity activation. So that's also super simple. And finally here in the output layer, we're just going to use a softmax activation. So this is a softmax. And let's look at this output here first, right? So here we have the softmax on the outputs. So the output here, since we're predicting labels, which are basically a vector, one hot encoded vector of a word, we're going to have one output neuron for every word in the dictionary. And so with softmax activation, just to remind ourselves from the videos on neural nets, so softmax activation means that this output is going to be, all the outputs are going to be non-negative and they're going to sum to 1. So we can think of it as a probability distribution. And this idea is that entry T in the output should give the probability that the word in the middle here is the word T given this context window, like the surrounding words. So if you look at the entry for who here, if we feed in partner, abroad, can, and accommodate, it should give the probability that the middle word is who when this context around this partner, abroad, can, accommodate. Okay. And in these neural net videos that we looked at earlier, we kind of drew this softmax layer just to remind ourselves what it is. We drew it as 2 layers, really. We have an identity activation here in the first one, and in the second one, like, so we had an identity activation here. And the softmax was basically doing, you have one neuron for each of the neurons in the previous layer. You take E and raise it to this value, divided by the sum of E to the raised to each of these zi's in the layer below. Right, so this is just a recap of what we saw. This is what a softmax layer looks like, right? We take basically the vector of outputs in the previous layer. We take every entry, E to that entry, divided by the sum of the E raised to the entries, just to make it a probability distribution. And everything is going to be non-negative because the exponential function is non-negative. Okay, so this is what's going to happen here, right? We're going to have an output neuron for every word in the dictionary, and maybe on this input partner, abroad, can, and accommodate, it's going to output a probability distribution, and maybe it looks like this, right? So probably it's very unlikely that apple is the middle word here, right? Partner, abroad, apple, can, accommodate. It's not very likely, but who is very likely here, maybe a 90% prediction of this being the output. Right, so you do the softmax, and if you wanted to, so that's the basic idea. So you train it to output a softmax here, and now we're going to use a loss function together with this, right? So we want to train this neural net somehow, right, to make these predictions. So we're going to use a loss function, and what we're going to use is the cross entropy loss that we also saw in the neural net videos. And so this loss function on a given point, if I have a label, so this is typically in setups where you have a machine learning model that outputs probabilities P1 to PD that sum to 1. And the intention is that each of these output probabilities should give the probability that the label is equal to a given J, given the features, the input features, right? So suppose this is supposed to represent the probability that we see who, and so forth. And so if we're in the setup and label vectors, this cross entropy loss works whenever the labels are themselves a probability distribution, a vector of length D with non-negative entries summing to 1. Here in our setup, right, our labels were just one-hot encodings of words, so they just have a single one in them, right? So they are already one-hot encoded. They're very simple versions of these vectors, a single one in some coordinate. Now, the cross-entropy loss then tells us it's a crossing of the entropies of the two distributions y and h of x, and it basically tells us that the pointwise loss on a prediction h of x against the label vector y is that you take the minus the sum over all the output coordinates, you take the yj, and the label in the jth coordinate multiplied with log of the prediction, the jth output prediction. Okay, and so what we see here is a special case where y is one-hot encoded, only one of these terms in the sum is going to be non-negative, so we're just going to actually do minus log of the prediction, the value of the prediction in this label that we have. Okay. So this is what the full setup of this model here, where we feed in one-hot encoded versions of these words in the context window, have a neural net with a single hidden layer here, identity activation, no bias, and a softmax at the output. And then we train this neural net on all this data that we generate, right? We generate all these training examples by just scanning through the text, and we're going to use cross-entropy loss here at the end against the true label who here and all these outputs by the neural net. We're just going to train it to minimize cross-entropy loss. And so basically the idea, and again, remember, if the dictionary has D words, then each of these groups here have D coordinates. And the basic idea is that once we've trained this neural net, right, so we're training it to make accurate predictions on the word in the middle. And the idea here is that we would like that I guess this middle layer here should somehow, similar to autoencoders, we would like that this middle layer, the output of the middle layer, should somehow give the embedding of a word. Now, the issue here is that how do we get the embedding of a word out of this when actually this takes 4 words as input, not just a single one? Right, so somehow we need to take this model that we have so far and turn it into a way of just getting the embedding of a single word here in the middle. Okay, so right, so if we had a broad here, then the observation is that let's just zoom in on one chunk here, like one of these batches of inputs where you one-hot encode a word. Typically, when we have these neural nets, right, we would represent the weights that are sitting on all these edges. We will represent them by a D by K matrix, right? One row for every input neuron, one column for every output neuron, and this matrix would be called W. So what happens is that when we feed in this one-hot encoding of the word abroad into this matrix, right? Typically, it's a row vector that we multiply onto the matrix from the left, as we saw in the neural net lectures. The only thing that's happening here is that you're just going to extract a row of W, right? So that's what we're going to get here in our output K. If we feed in a one-hot encoding of abroad, you're just going to get the corresponding row of the matrix W, right? So the matrix W has one row for every word in the dictionary. Right, so it's going to look like this, right? So let's say that abroad is the first word in the dictionary. So it's represented by 1, 0, 0, 0. If we multiply it onto this weight matrix here, A, B, C, D, E, F, G, H, just going to extract the first row of it. So the idea now is, or the intuition to keep in mind is that each and every one of these rows of the weight matrix somehow gives the embedding of the words in the dictionary. Okay, that's the intuition. But now the problem is we have 4 of them. So we basically, in some sense, we have 4 different representations of all the words in our text, right? So that's kind of annoying. So the solution, I think that's the small tweak that we're going to do to this is that we're actually going to force the same weights to be used in all these 4 chunks. So basically that we have the same representations of the words. So basically we're going to use the same weight matrix in all 4 chunks. That's the kind of idea. And we have another weight matrix over here. This is not necessarily the same. Okay. So we can, of course, train this. And if you think about the backpropagation algorithm, it doesn't matter that there's weight sharing. You can easily have the same variable occurring in multiple places. That's no problem at all. But there's a small observation that we can maybe use here. So the output of the middle layer, if we go back and look at this picture here, right? So there's identity activation here, right? So this means that since these are computing linear things, the observation is that the middle layer, what it's going to output is, well, it's going to just output the sum of what it would output if we fed in the representation of the first word into the first chunk, the second word into the second chunk, and so forth, right? So it's just going to output this. And by linearity, we can write this as having W over here and then summing up these one-hot encodings of the words that occur in the context window. Okay, so this means that we get there's a simpler way of representing the training data. So instead of actually having like 4 separate chunks with inputs to our neural net, what we're going to have is we're just going to have one chunk with one neuron per each of the words in the dictionary. And then we're just going to sum up the one-hot encodings of the context words and use that as our input features, right? So we're just going to sum up these 4 one-hot encoded vectors. So now we have a vector with 4 ones and the rest are 0, and that is our input feature vector. So now it's only length D, not length 4D. Right, so that is what we're going to do. We're just going to have a W here. And now the input is going to be the sum of the one-hot encodings of the 4 words in the context window. And this is our final, I guess, architecture of our neural net that we're going to train, identity activation here. And this is the way we're going to represent all these context windows. And we're just going to use a softmax activation here at the output and use cross-entropy loss against the label. And we're going to train this on just all the training documents, right? We're just going to scan through all the training documents, and for every word, we're going to take the context window around it and generate one training sample, and just train this neural net. And the way we're going to train it is just using mini-batch stochastic gradient descent, like we always do in these cases. Good. So finally, once we've trained it, we can now obtain the embedding of a word. And if I have a word T, all I'm going to do is I'm just going to take the one-hot encoding of T and multiply it from the left onto W. So basically that gives us the representation here in the middle layer. And basically this is the same as taking the Tth row of W. So really what's happening here is that this W that's sitting here as the input At the end of training, W will just have, as its rows, will have the word embeddings of all the words in the dictionary. And the hope is that if we're training this neural net to predict the middle word from the context, then these word embeddings should have good meaning. They will, actually, because here at the end, right, these are the features that are being fed into W1, and we're trying to train the last part of the network to accurately predict the middle word. There should be some meaning to these words. So these representations should somehow capture the meaning of the words. And this is the basic intuition in continuous bag of words. So this is what we get out. And this is the continuous bag of words representation, where every entry now here, every row has k entries, one for each and every one of these neurons in the middle layer. And maybe you typically choose, I guess, this k to be maybe a couple of hundred. So that's the continuous bag of words representation.